Okay folks, today we're going to look at loci on a complex plane, okay, which will be the final part of complex numbers. Okay, so sometimes we have to find the locus of a point which moves in the complex plane with restrictions placed on its modulus and argument. So what this is going to be, we're not going to know exactly what a complex number is, but if we're given a bound on it, a restriction on it, what could the possible solutions be? Where could this complex number lie on an Argand diagram, for example? Okay, or what equation could it maybe lie on? Okay, so we'll start with our first example. So given that z equals x plus iy, we're going to draw the locus of the point which moves on the complex plane. Such that, and this is what I mean by the bound, the only restriction we've got for this complex number is that the modulus of it, the size of it, okay, has to equal 4. Okay, so that's what we've been bounded by. Okay, so we know we want to find the possible region for where a complex number could lie such that its modulus would be 4, could be one of the solutions for this question. Okay, so the good thing is that, well, we'll start with the solution part here. So if we know the size of z is 4, then we know the size of z relates to r, it's the modulus. Okay, and if we remember that r, how we work out r is the square root of x squared plus y squared, okay, are two numbers that are attached to a complex number, which means that the square root of x squared plus y squared is 4. Okay, in this question, okay, because we've been told the modulus, okay, is 4, therefore the size of r has to be 4 as well. Okay, so we've got that there. Now, if I square both sides, okay, so what I mean by that is if I square the square root and square the 4, it leaves me with x squared plus y squared, not equals 4, my apologies, equals 16. Okay, so that's what I get if I square both sides. Okay, what I now have is an equation of a circle. Okay, I've got an equation of a circle such that the centre would be at 0, 0, okay, because no deviation away from the x or the y. And if I take the square root of 16, then I've got my 4 back in, so I know the radius would be 4. Okay, so this is where it goes a bit haywire for me. So this is a circle of radius 4, centred at the origin. Okay, and obviously your sketches will be a lot better than my bad ones. Yep, that's very bad. But then we know the radius would be 4 and 4 there. So basically, our complex number z could lie anywhere on that circle. Okay, that's what we found. Okay, there. That's the region on the Argand diagram. Okay, that it would be. So if we swap x for the real and y for the imaginary part, that's where our complex number could lie on anywhere along there on that circle. Does that make sense? Okay, so that's what I mean by locus. Okay, as we found a bound, we found a region on the Argand diagram that z could be anywhere on. So any z would satisfy that bound. Okay, as long as it was on that unit circle, on that circle there with radius 4. Okay, so okay for that first example? Okay, so that was quite a nice one regarding the fact when we dealt with the modulus, we got a nice circle out of it. It was centred 0, 0. Let's have a look at another one. So let's look at example 2. Okay, so again, if z equals x plus iy, then part A, find the equation of the locus z minus 2, the modulus of, equals 3. Okay, so that's part A. Okay, so we've got z minus 2. And then part B, we're going to draw the locus on an arcGAN diagram. Okay, so we're going to do that, we're going to draw it on an arcGAN diagram. Okay. So, again, this question here, they gave us a bound, they gave us a restriction on the size of the complex number. Yeah, they're telling us this, the complex number has got to be, well, the size of it minus 2, I should say, has got to be equal to 3. Okay, that's what it's telling us there. So, let's start us off with that fact there. So, we've got z minus 2, the size of equals 3. So, I've got to try and find a complex number such that, or a region for complex numbers such that if I subtract 2 from it, to get the size of it, the size would be 3. Okay, so that's what I'm trying to find here. Now again, we know what z is, so we can write that down as x minus 2 plus iy. So we know z is x plus iy, but the reason why I put the negative 2 closer to the x is because negative 2 is a real number, and so is the x. The x is a real part of the imaginary number, okay, the complex number. Therefore, it's going to affect the x, okay, it wouldn't affect the iy part, okay. So, what that means is, okay, I can now say that this thing here equals 3, and now using the fact that the modulus is r, okay, so because we work out r like this, then here, it's going to be not just x, but x minus 2 all squared plus y squared. Okay, I'm grouping the real part, and then I've got the imaginary part. I need to square them both to get the size of r, and we know that has to equal 3. Squaring both sides, the x minus 2 in a bracket all squared plus y squared equals 9. Okay, so I've got that there. So that's part A done. Okay, I've got part A done. Okay, so part B. So this is a circle now. With centre well, where from higher, centre of the circle, okay, so it's going to be 2. We've went away 2 from the x, and we haven't deviated from the y, so it's 2, 0, with radius 3. Okay, so we've now got a circle that's got a centre 2, 0 this time, with a radius of 3. Okay, and again, let's sketch what that would look like. Again, I'll do a very bad job. So let's say 2 is along there, so the centre of my circle there. Well, I know my radius is 3, which means I'm going to have to go along 3 to find the end of it, so that's going to be along at 5, minus 1. Again, very badly drawn, but something like that. Okay, and that's the locus for that one there. Okay, so the complex number would be somewhere along that circle there. Okay, we've got a bound. You okay with that example? Alright, so we've seen that just when they had a minus in the z, we've got to take the bit that we're taking off the right part, whether it's a real number or the imaginary part. Okay, and again, we would do that there. So there's 2 examples that the bound's been related to the size of it, the modulus. Okay, we're going to look at a bound now that's related to the argument, which is the angle part, the theta part. Okay, so we're going to think about that there. So example 3, for example, if z equals x plus iy, then we're going to find the equation of the locus such that the argument of z equals pi over 3. Okay, so you want to find the equation such that the complex number, the argument of that would be pi over 3. Okay, so that's what we're saying there. Okay, so let's start us off with the solution here. So if we know the argument of z is pi over 3, then how we get the argument when we done the polar form was we used tan. Okay, therefore it means that the tan inverse. Okay, so again I'll give a quick sketch just to remind ourselves what we're talking about here. So if I've got a complex number, say for example over here, and I want to get the argument theta, okay, then we use the triangle. Remember, this distance was always the y, and that distance was always the x, wasn't it? Okay, so therefore here, to get the argument, it was always the tan inverse of the distance of y divided by the distance of x. Okay, so that's what that is there. And we know that there has to be pi over 3. Okay, so that's what we've got there. Okay, so if we now take tan of both sides, so therefore I get y over x, that equals tan of pi over 3. Okay, and if you use your exact value triangles, tan of pi over 3, that's root 3 over 1. Okay, which is just root 3. Okay, now this question asks me to find the equation. We always start the equation y equals, therefore if we bring the x over, the equation will be y equals root 3 x. Okay, so any complex number such that it's got an argument of pi over 3 has to lie on the line y equals root 3x. Okay, it has to be along there somewhere. Are we okay with that? Okay, so that's an example of when a question is bounded by the argument.
So is that one just a straight line instead of a circle?
Yeah, that'd be a straight line, exactly. Okay, it'd be a straight line because the angle has to stay the same, so that's why it would just run along this straight line. Okay, as opposed to going round an argument that we're bounded by the size of. Okay, do you want to have that? Any other questions?
No.
No. Okay.